Hey guys, I'm back. So today I'm doing something a bit special. I have the green screen behind me. As you can probably see, you're going to see pictures of the Standerd Model. I see green paper. So today I'm going to be talking about really what particles are and the interaction between particles. Now, we all know there's several classes of, I talked about this in an earlier video in the series of the Standerd Model, but we all know there's the classes of particles, right? You have the quarks, the bosons, and the leptons. So, what are quarks? Well, quarks, you have this, the 6 quarks, up, down, strange, charm, top, bottom. And, well, there's also 6 more quarks with the anti-up quark, the anti-down quark, the anti-strange quark, and the anti-bottom quark, and the anti-top quark, and the anti-charm quark, and whatever other anti-quarks I forgot, but all those quarks anti. And so to summarize, really, what is an up quark? Well, an up quark, I have my notes here, so that sometimes I forget. An up quark has a 2/3 charge. 2/3, right? So this is a fundamental electric charge, one of the quantum numbers. I have a quantum number video that you can watch to get more information on this. And so this is going to be important because the down quark, by comparison, has a -1/3 charge. So the down quark has half negative charge of the up quark, meaning that if you have 2 down quarks and 1 up quark, they cancel each other out. And this is what you find in particles like a neutron. That's how they get their neutral charge, is they have 2 -1/3 quarks and 1 2/3 quark, which gives them the extra, like, no charge. And by comparison, a proton will have 2 up quarks and 1 down quark, which is 1 -1/3 and 2 + 2/3 charge. And so this will give you a positive charge of +1 because you have the half of 2/3, which is 1/3 charge, which the down quark cancels out from the first up quark, and the second up quark will be that charge added onto it, which gives you 1. So this is the way these pairs, all the quark pairs, or generations as they're known, first generation of up-down, second generation of strange charm, and third generation of top-bottom, those generations are have the same charge, +2/3 and -1/3 charge, which really forms normal matter as we know it. So now to talk about the interactions with the quarks. So if I step away for a moment, you will see that this diagram where you see the gluon, which is the carrier for the strong force, is coupled to itself and coupled to the quarks as well. Okay, so this means that the only particles that the gluon could possibly act on are the quarks. So if I step back in the frame for a moment, you'll notice that the quarks are the only particles acted on by the gluons. Now the gluons carry the strong force, and this strong force is the force that is the strongest force that we know of, probably, that exists, but always we could discover some super strong force, probably call it that anyways, because we love to give silly names. So that means that the quarks are the only particles that take part in the strong force. And the strong force is very, very, very strong. It's so strong, in fact, that it forms particles like 10 to the -20th seconds is all it takes. If you have 3 quarks floating around, in 10 to the -20th seconds, those quarks will be turned into a particle, a baryon, or baryon, or however you pronounce it. I don't really know. Never pronounced it correctly anyways. So it's a very strong force. And this is carried, if you're talking about individual particles, by gluons. If you're talking about atoms, it's carried by mesons that I'm not going to get into. But anyway, the gluon, you're going to see a little correction loop in the gluon, right? And this loop goes back to itself. This means that the gluon is influencing itself. It's acting upon itself. And so this means, and now what do I say acting upon? Like, the quarks are subject to the strong force, they take part in the strong force. What do I actually mean by this? Well, what I mean by this is that the quarks, when they're floating throughout space, right, there's a virtual field. You can look up quantum fields. I have a video on that explaining this. But there's a virtual field of gluons. It coats the entire universe, not a place in the universe without this field that we know of. But, ask your astronomer. It'll be in the news if we find out a place without gluons. But basically, this means that wherever in the universe you go, there's this virtual field of gluons coating everything. It's everywhere. You can't get around it. And when we say something takes part in the strong force, it just means that while it's going through space, the gluons are interacting with it. The actual particles are touching each other and grabbing onto each other and bouncing off each other, dragging each other behind, whatever interactions you want, bouncing off each other, exchanging properties, what have you. That's what I mean when I say it takes part in the force, is that it'll interact with those virtual fields that go all throughout space. And it doesn't just, if it's strong force, it can act with the virtual pion fields that go throughout space, the virtual kaon fields, I think, is another one for atoms that will take part in the strong force. But when I say it takes part in the force, I mean that while it's going through space, while a particle is traveling through space, there are particles, those gluons or whatever particle happens to be, photons, it doesn't matter, are the virtual particles in the virtual field are attracted onto it. And normally, if you're in physics class, you won't see this explained to you. You'll see a Feynman diagram, and maybe or maybe not, for example, most students will see photons, and so this you'll see these extraneous lines coming in. Maybe you want squiggly lines to represent bosons, which are photons, and these may or may not be represented, but they probably won't be talked about in your class. And this is because these are the virtual particles in the field, and that means that you generally don't account for these because they're everywhere. They don't come from anywhere except for the virtual field, and they don't lead to anywhere except back into the virtual field. So they're really not discussed, but that's what we say when something is a force carrier. It means that that field goes the entire universe, and that the interactions between that particle and another particle result in what we call the force, or whatever force it happens to be. So now I'm going to talk a bit about leptons. This is something that a lot of people are, iffy on. And so they don't really know what a lepton is. They probably saw it in some TV show where they're using fancy words. And so all it means is it's considering the neutrinos and the electron-like particles. So the neutrinos, you have the electron neutrino, the muon neutrino, and the tau. And you have, for the electron-like particles, you have the electron, the muon, and the tau. And, to check my notes, there is zero charge for the neutrinos. So the neutrinos don't have any antiparticles. If you see an antiparticle and it'll say, like if you're looking up on the Wikipedia page and it has a little listing for antiparticle and it says self or none, this is basically going to mean that it has zero charge, and since an antimatter particle, the only difference that we know of so far, well, LHCb is looking to see what's happening with this, if there's CP violation. But so far, the only difference we know of is that there's just a negative charge for the antiparticle. And so, since there is no charge, there can't be an antiparticle for the neutrinos. The electron-like particles, on the other hand, all have a -1 charge. The electron, the muon, and the tau all have a -1 charge. And so this is, and basically the electron, muon, and the tau are all like each other. They're almost exactly the same, except each particle has increasing mass. So the electron has a very small mass. Muon has a relatively, pretty good mass. And then the tau has a very large mass. And also proportionate to those masses, the particles decay faster and faster as you get up to the tau, which decays pretty fast. And so those particles, there's really not too much to talk about. I mean, obviously there's quite a bit to talk about, but most of us probably know a lot about the electron. This is the particle that goes throughout your electronics and flows through those systems. And really the muons and the taus will act very similar, except they don't live long enough to do anything. Really, they have a very short lifetime compared to the electron, which has a much longer lifetime. And so, yeah, that's those particles. And so, then we can get on to the bosons. Now, you have photon, gluon, Z boson, W boson. I talked about these in the other videos. But if I step out of the frame for a moment, you can see how they all interact to each other.